Good morning, everyone. My name is Nurassyl Battalgazy. I'm a second-year PhD student at Bryan Mining and Geology Research Center, Sustainable Minerals Institute, the University of Queensland. And today I'm going to talk about application of machine learning and deep learning in resource estimation. So the outline of my presentation is as follows. First of all, I will give a brief introduction and overview of the methods, and then we are going to talk about the specific data and convolutional neural network method, and then we will discuss the results and comparisons and future work, and at the end I will conclude. So in every mining project in both open pit and underground mines, 3D modeling of mineral deposits plays a key role, as it may result in positive or unfortunate consequences on the downstream activities such as production schedules, mine design, optimization, resource estimation, grade control classification, and cash flow of the project. And usually block models are constructed by various methods depending on the available data and the characteristics of the ore body, but due to time limit, I'll not go in details about conventional methods. But in overall, spatial prediction of ore body characteristics by traditional geostatistical methods can often be challenging in deposits with complex geological structure. And the issues are high nugget effect, assumptions made, geological disturbances, and insufficient dense drill holes and nonlinear complexity, which are the main related issues. And machine learning and deep learning can be an effective alternative to address these issues, since neural network can handle complex nonlinearities, so there is no necessity of experimental variograms. And machine learning and deep learning are branches of data science in which computer is focused on building algorithms that learn from historical data by finding features to make predictions about the new data. So one of the main objectives of this research is to build an intelligent system that will search for patterns to understand the characteristics of the data set, so that it is used in predicting ore grades on unknown samples. And that will also follow the distinctive attributes of ore body, like geology and structure. We used XRF image as the data, and there are several reasons why we used it. First of all, XRF from whole rock samples produce 2D maps of elemental composition and mineralogy, so we can use different quantification methods. And also, XRF image shows similar characteristics as in real size geological structure by representing the vein type and vein type shape and faults across the veins as shown in a figure. And finally, knowing the ground truth, in our case it's all pixels, allows us to validate machine learning, deep learning, and other techniques by comparing the predicted and actual numbers. So there are 5 different methods that we used: support vector regression, multi-layer perceptron neural network, which are machine learning techniques; nearest neighborhood and simple kriging, which are geostatistical conventional methods; and convolutional neural network, which is a deep learning technique. So turning to convolutional neural network, this is the model that we used. The model architecture is composed of contracting and expanding paths interpreted as encoder and decoder. The encoder part takes images with missing data, in our case it's 90% missing data, as an input, and computes future maps at different scales, resulting in multi-level pattern representation. And the decoder part synthesizes the complete data, in our case it's ground truth data, as an output, starting from low to high resolution associated feature maps. And then before starting to work with CNN, training images need to be prepared. So there is a widespread agreement that successful deep neural network requires a large number of training images. But in this case, the whole XRF image of potassium was used and split into a number of images by the size of 256 to 256, as you can see from these images, to teach the CNN acceptable robustness data was augmented, and the total number of training images after augmentation reached 1,276. And the input and output of the training images are shown here. On the top, you can see that 90% of the pixels were masked by removing each 9 columns of pixels iteratively. So we were just trying to imitate the drill holes. And turning to results, these are the results from different methods. And as you can see, the top left is the ground truth, and the rest is predicted maps of potassium based on different methods. And we can see from these images that CNN shows the best results in terms of reproducing the vein type shape and associated faults. This can be explained by the fact that CNN model learns from training images and captures important features of each training image based on thousands of calculations and analysis. And other methods like support vector regression, nearest neighborhood, and kriging has showed similar results. However, they are not able to reproduce the regions with the faults. And a multi-layer perceptron in this case failed in even following the shape of the ore body. And it should be mentioned that the noisy part of the CNN can also be removed by using image segmentation methods in the future by CNN. And this is another result which shows the difference map, which shows basically the difference between actual and predicted map. By looking at these maps, we can see that CNN has less differences, particularly in fault zones. This is the same result but focused on ore zone or ore body zone. So it's basically done to compare results in more appropriate way, because in case of hole maps including waste zones, we are calculating unnecessary waste zones, which leads to pseudo better results or worse results. For instance, imagine we have a map with 90% waste and 10% ore, and we are classifying whole map as waste. So the result will be 90% accurate. So that's why it was important to cut the waste zone. And after cutting the waste zone, this is the results showing the table showing the RMC and R2 score. RMC is a measure of differences between predicted value and true value, and R2 square is a coefficient of determination, which is a statistical measure in regression model. In other words, it shows how well the data fits the regression model. And we can see from the table that CNN and kriging shows almost a similar results, which is a good indicator for CNN, and possible usage of more training images in the future may result in better performance of the CNN methods. So this is the future work. As I said, it's better to use more training images, so we will focus on that. Then we are going to try multi-input, multi-channel CNN, so we can use additional information such as other elements, lithology, mineralization. And of course, we need to end with a 3D block model. So to conclude, as traditional exploration industry is moving towards a more data-driven approach, machine learning and deep learning are very promising approaches for solving data reconstruction tasks and have huge potentials in resource estimation. And as we could see from the results, CNN performs effectively better in reconstruction of faults and shape of the ore body and has high potential over conventional methods. And contribution to sustainability. The application of these methods focuses to make block models more accurate, which will decrease the energy usage, human resources, and environmental effect of downstream activities in mine life cycle. And more accurate design of pit, which is designed based on the block model, will reduce the amount of energy used to extract ore and waste. So this is the end of my presentation, and this is a reference. Thank you for your attention.